will those people come back or they will go? Then we can start. Curl. Okay. So curl. Many people ask me this question: how to visualize curl and whether to read Feynman or not. Feynman is a human being like us. If he can think what is a curl, we can think. All of us can. Now you will think in front of me what is a curl. So if given a vector field A, the curl of the vector field will be a vector, and you know the formula. Okay. I am just writing the z component of curl. What it will be? See, this kind of things, to get used to this kind of things, you will take a little bit of time. How I just wrote down the formula. I didn't remember. It's a cross product, right? Forget about determinant and all. It's a cross product. So first into second minus second into first. So first is a derivative, right? So del by del x. And when we define cross product, we should go from x to y to z, and y to z to x in right hand direction, right? Not in the left hand direction. Fine. Okay. So this is the z component of curl. What does it mean? So this is my x-axis, this is my y-axis, this is my z-axis. So the z component of curl is a function which is, if I move along x, how ay is changing. Ay is this height, right? So if I move along x, how ay is changing. Suppose ay is changing in a continuous fashion like this. These are not vectors, they are lanes. These lanes are changing like this. As we move along x. Taking derivative means what? You move along x and see the function. How it is. Minus, if you move along y, how x is changing. So suppose I move along y, my x components are also changing similarly, same length. This length are same. Then what is happening? Look at the vector field. The vector field is such that the vector field will be this way. So the vector field is such that the y component is trying to increase and the x component is trying to increase in this way. So there is no net increase and the vector goes in this direction. Fine. So it is as if one component is trying to rotate, another is trying to rotate, and they are balanced. If they are same, if these two are same, and both are positive. Fine. Here both are positive because y is in y-ward direction, x is in x-ward direction. Now what if the second quantity is negative? The second part is negative. Means x is in this direction. Negative x. So ax is negative, so this quantity is negative. So both is positive. So what does it mean now? This trying to rotate here, this trying to rotate here. So what happens to the field? The field is like a rotating, right? Similarly everywhere, right? So if the net curl along z direction, it means a rotation in this direction, counterclockwise. Had it been in negative z, clockwise. Similarly x and y. This is what physically curl means, nothing else. And this we can think or not, right? So we did not read any book. Yeah.
Suppose in a thing is sloping and it's also moving in clockwise direction.
So yeah, very good. So you can have a vector field which is both diverging and curving. True.
Like the waterfall.
Yes. Then, see, so what he's saying, you have a vector field. Is not 0 and delta cross B is not 0. This is very much possible. And in 10 minutes I will show you what kind of example of such a field, which is both curling and diverging. Like somebody said and I said no, because I was trying to say going away rather than going in, always negative. Like water spiraling in, we were saying. Okay? As it goes, it's going towards the sink, right? But it's not going directly. It's diverging, it's converging, negatively diverging, but still it's curling also. This kind of fields exist. Okay. So curl is also clear now. And the two important theorems, which we will not prove and we will see physically. Well, I didn't tell you an application of divergence, which I will tell you now. There is an equation in electromagnetism which is called Maxwell's equation, which is this. You may not have seen this version of the equation, but trust me, we will derive this equation in 10 minutes. Okay? That's the last part of the problem. Given this equation, this is the nature of electric field. Given an electrostatic charge, a charge which is static, not a point charge, but some charge distribution. That's why the density. This is charge density. Okay. Then the divergence of electric field is just charge density. Pi epsilon naught is a constant. Okay. What does this mean? we will discuss, not now. So I just say this is the while we are defining divergences and curves, you will see now. I am giving an equation that this is a law of nature. This is a law, and this law is written in terms of divergence. Okay. Similarly, there are laws which are written in terms of curls. We will see now. First, I will write two theorems on divergence and curl. First theorem is divergence. First theorem is divergence. I always expect a lot from me, but I am never able to do it. I wanted to derive all the Maxwell equations for that because the teacher has given me. It's stop, but I can't derive. So 1-to-1 correspondence. Whoever has doubt. Divergence theorem says we will not prove it because the proof is really tough. I mean, not tough for anybody who is a 4th year or 5th year student because they have done it in calculus several times. But I will show you what is the meaning of the theorem. The theorem is divergence of any vector field, volume integral. D tau means a small volume. I don't write dv because you will think a small velocity. That's okay. Is equals to integration of a dot d. Gaurav, I think I'm writing big things, right?
That's fine. It's fine.
You can see it.
Resolution is fine.
Huh? Yeah, I'm going. So divergence of a vector field in any volume, in any volume tau is equals to the dot product of the vector field with the area in small area. I will define everything on the area. What does it mean? It means if I have a volume, okay, then divergence is a function. It's a scalar field, right? Divergence of a vector is a scalar field from phi of x, y, z. Here, if I go to a small volume d tau, find the divergence there. Then go to another small volume d tau, find divergence there and add them. This is the meaning of integration, right? Add. That will be equals to a dot ds. So I will come to only the surface and see what is the vector field on the surface. On the surface only, yeah. Look at this. This is A on the surface here. And what is the direction of area? This N. ds is a small area element which is ds into n cap. N cap is a vector which is perpendicular to area. These things you know, na? Right? I assume these things you know how to define area as a vector. Area is a scalar. To define it as a vector, you put a direction which is perpendicular to the plane. Okay. So now A dot dn. So A dot dn is A cos theta, right? So this is theta. True? So A dot dn is A cos theta. So which is coming out from the surface which is perpendicular to the surface. And what about the component which is parallel, that is not appearing here. Right? We are only taking that component of A which is perpendicular to the surface. Now what does it mean? It means if there is, this is called a flow of vector. If I have a vector field, divergence means flow, right? It's flowing out. So the flow of a vector field in a volume, whole volume, is equivalent to the vector field coming perpendicularly out of the surface. Because if it is parallel to the surface, it's not coming out. It's not flowing. Flow out. So the flowing out of a vector field is equals to the perpendicular component of the vector field on the surface. And why closed? Because if I have a volume, then the surface is a closed surface, right? Otherwise I can't define a volume. If I take any volume, any cell, the whole surface is a closed surface, closed. Okay? So you understand now physically what it means? So if anything is flowing from inside the volume, then it must come out perpendicularly from the surface. If it is parallel to the surface, on the surface only, it's not flowing out. Fine? Then another theorem, which is called Stokes theorem. I don't like these names, which I call curl theorem. Because I don't know whether Stokes first found it or some other mathematician like this found it or somebody found it. Call ds on the surface and find what is the curl of any vector field on that surface. See, a vector field is a function, right? A vector field is a directional function. At every point you have a function. So you find what is the curl in any small area. Then you find in next area, and add them. This is the left hand part, which is equals to the vector field on the boundary, which is equals to this dl is this length, the boundary. Okay, is the boundary. If I have an area, if I have any kind of surface, I have a boundary, right? So dl is along the boundary. Fine. So listen this carefully. So a dot dl means along the boundary, while a dot ds it won't go away, right? And the part which goes away is not actually rotating; it's actually diverging. Fine. So the part which is going away, we just throw it by making a dot product with dl, and only take those part which is along the boundary. Fine. If I rotate it, the net rotation. Why this is true, I don't know. I mean, for now you don't know why this is true. Why this is exactly equal to this? Why not there is a half factor? That is mathematical proof. But I am interpreting the equations. The interpretation is the net curl on the surface is equivalent to the net rotation of the vector field on the boundary. That's all. Fine. Good job. I have to stop now, or can I just derive one or two Maxwell's equations for that? 3 Maxwell's equations I will derive. The 4th one is your homework, which is very, very tough. But then you have to using some kind of a convention. Remember, everybody who wants to be a physicist, I am using a convention which you will use in physics forever in your life. I will explain this concept. This is not a concept, this is a mathematical notation, but in terms of an example. Now suppose somewhere in the space there is some current flowing and there are some charges, like a charges, but they are continuous. Now what is a continuous current and what is a continuous charge? A continuous charge, you know, charge per unit volume is defined, density is defined. You have a continuous distribution of charge, which is actually not true, as you know, right? Charges appear as electrons and it's not continuous. But if you are studying a big system, then we can see it as a continuous. Actually, this is not even continuous. We say that this mass is continuous. Actually, this is not continuous. There are atoms here and there, electron and proton. From proton, electron is very, very away and away. So if I have a continuous charge distribution, then density at any point is equals to dq by d tau at that point. So charge per unit volume. In my notation, tau is always volume. Please don't confuse me. When I give my notes, everything will be written. And then how to define a continuous current? There are ways to define. See, suppose current is flowing in this way. I know current is dq by dt. Fine. Now suppose there is a big wire. Have you seen those big wires? The telephone wires which are red in color. The telephone wires which are red in color. There's so many wires coming out, so many current is coming out, right? So I can define in a small area how much current is coming out. So I can define, you know, I think in 12th class also you use this. So D, I call it J vector, current per unit area along a perpendicular direction. So how much is perpendicularly flowing? Correct. These two concepts are fine. Now so I have some J here, some rho here. So I will have some electric field and magnetic field due to this. If I have charge, I have electric field. And if I have current, I have magnetic field. Fine. So due to this source, at some point from me, I am sitting here. I am a guy who is looking at the wall. I am sitting here, some source is there, and I am finding what is the electric or magnetic field of that distribution at some point in the space. So I want to calculate here. I call that as R cap, small r cap. Remember, small r cap is the point where we want to find the field. Fine? And this we call a source, which is causing the field. The field here is caused by this source, right? So I go to some small volume here, and I call it R dash. Remember this notation, you will use it everywhere. And those who are following Griffith's electrodynamics book, they will always get confused if you don't listen to this, what I'm saying. Whoever is sleeping, let them sleep. And if this is R dash and this is R, then this is R minus R. Fine? I call it curly R. Okay? So the value of field here, should it depend on my position? No, it should depend on what is how much source is away from the point, right? The value of electric field here doesn't depend on where I am sitting. It depends on where the charge and currents are sitting, right? So the value depends on curly R. Doesn't depend on just R. Fine? This concept is clear, right? Because the field is caused here by this. I can sit here also. But then R changes and R dash changes. But curly R will be the same curly R. So I am going to a small volume and seeing what is the electric and magnetic field here. Then I am going to the whole volume by doing integration. The concept is clear, right? Then what will happen? What is the consequence of that? You people all know Coulomb's law, right? So if there is some small charge, excuse me.
ଟିକେ ଛୋଟ ଏଇଟା ଦେଖୁମାନେ ଚାଲେ एक्चुअली मैंने कुछ कहया था अच्छा यहाँ पे जो सब वॉलंटियर्स हैं फर्स्ट ईयर के तू है ना उसमें वो ये खत्म होने के बाद थोड़ा ऑडी थैंक यू
what is your big day, right? The only batch in NICER who didn't have a freshers party is our batch, 2008. So we gave ourselves a freshers party in 4th year. Okay. So if this is a small charge, I can think a small volume as a point charge, right? So due to this small charge dq, what will be the electric field here? From Coulomb's law, right? I write D because for the small charge dq. Please let me know if you don't read my handwriting. dq by curly r square. That is the important thing. Curly r because that depends on the distance, right? This is D. Now what is dq? dq is rho theta. Fine. Whatever be the density here into theta into the volume. So I make the notations now clear. This is rho as a function of r dash. Why? Because rho is my dash is pointing points on the source. So source variables depend on r dash, and field variables depend on r. Because I am finding from me at what r, at some r, what is green. So given r, what is E? That depends on where is my source and what is the distance of source. What is the distance of source from field? This is clear? Fine. So the direction will be some. True? Very good. It's a vector. The vector is in this direction, right? if here, what is the electric field of this charge? It's in this direction. Now what I will do? So E at any r is equals to 1 by 4 pi epsilon naught. All of this you will do in next semester. Please listen to me carefully. Don't write. Rho at r dash d tau dash by r minus r dash mod square. Is it clear? Curly r is r minus r dash. Right? R dash is the coordinate which is pointing the sources, and R is the coordinate which is pointing the field where we want to find it. Clear? This is the notation in physics you will follow in whole of the life. Now what I do? I take a divergence. An integration is very good. Thank you. The integration is over that volume in which the source is present. We have to take all the sources, right? Now, given a finite source, can I integrate over all volume? The answer is yes, because if I go to a point where there is no source, I get 0. So adding 0 is not a big deal. Integration means adding, right? So I can say this volume is whole volume everywhere in the universe, so that wherever is the source, because the rho r dash will be 0 if I go away from this point. If I am here, this is my r dash. This is my r dash. What is the field due to this point at here? Is 0, because there is no field there, no source there, right? So I can integrate over whole volume. I am integrating over source. Remember, I am integrating over source. I am taking a small source and adding all the sources in the water. So I can also add zeros. Fine. So I can integrate over whole space. This point should be clear, because this we will use. If not clear, please ask me. If my source is only here, this is my domain of integration, the source. And non-zero domain is only where source is there. If I take a point which is outside the source, it will give us 0 always. So we can always take it, because integration means adding. If I say what is the value of electric field due to this sphere here, there is some value which is also equivalent to this sphere plus this much space with nothing charge. True? Which is exactly equal to this sphere plus the whole space without any charge anywhere. True? That's what I am doing. Why I am doing this? Now I take the divergence of this. The divergence, this notation is very important. Divergence is a divergence of E. E depends on R, and divergence is with respect to R. So as I change R, how my electric field is changing. And remember, divergence is a partial derivative, del by del R. Right? So when I am changing R, I shouldn't change R dash. Fine? So if I take divergence, the divergence will go inside. Will the divergence act on this? This is a function of R dash. The divergence is with respect to R. So this won't act on this function, right? So this function just stays out. So I get delta dot E, I will get out of the middle, is equals to 1 by 4 pi epsilon naught integration of rho is outside now, not outside the integration because it's still being integrated, but outside the operator, rho and r dash into divergence of, now I am wrong, r cap. True? I wrote there r cap. Lower effort. Is this true? I told you r cap is all the time changing. Not like x cap, y cap, z cap. So I have to take the derivative of r cap also. I cannot take r cap out. R cap is not a constant. As we move here and there, r direction is changing. So as a vector is changing. But x, y, z are always changing. Now I am gone.
Prime, d tau prime.
Yes, prime. Very good. Thank you. No, why not?
No, on tau.
D tau. Yeah, thank you. But this I can change to prime and to the minus. Yeah. Now I didn't introduce dirac delta function. Kill me. Okay. The result of this integral, remember this quantity is called delta of R. It's a kind of, I take this and put there. So here, if this is equal to integration of J of n cap d. Fine. So I dl equals to J dot n cap dA dl. This is J data. Fine. Here I was a constant current. No, I was a constant current. What?
I equals to integration J dot n dA dl.
Yeah.
Just substituting I dl, I will get integration, right? Double integration, because you also have two limits.
What are the two integrations? What are the two double integrations? First is over tau. What is the second? Same tau. A is not being integrated.
No, it is being integrated.
Okay. I got the idea. Okay. Fine. Okay. So this is my I, whole I. Or okay, I got the idea what you were saying. So actually here we are not changing the area. So I should have written like this. I equals to small I equals to J small area, but again you think it's changing. I equals to J into A if J is constant. To get I have to integrate over area. Fine? But if my I is constant, then J just comes out. If I is constant, then I don't have to integrate, right? If everywhere I is constant. Sorry, J is constant. I dl should be J beta. Whether it's true or not, let's check. This is equals to di by dA. Fine? Into deta. This is equals to di by dA into dA dl. Fine? Now everything fine. And I can put a yeah.
Now it's di dl equals to by
Yeah, that is true. But I direction and dl direction are same. So I can call one I and
mathematically it's not. One on one side you're having a double integration, on the other side you're having a single integration. I mean, I won't accept it.
flow. So the flowing out of a vector field is equals to the perpendicular component of the vector field on the surface. And why closed? Because if I have a volume, then the surface is a closed surface, right? Otherwise I can't define a volume. If I take any volume, any set, the whole surface is a closed surface, closed. Okay? So you understand now physically what it means? So if anything is flowing from inside the volume, then it must come out perpendicularly from the surface. If it is parallel to the surface, on the surface only, it's not flowing out. Fine? Then another theorem, which is called Stokes theorem. I don't like these names, which I call curl theorem. Because I don't know whether Stokes first found it or some other mathematician like this found it or something. There was a small refute in the lecture at the last part of the lecture where we were deriving Maxwell's second equation on the curl of B, and so we would like to clear it up at the last of this lecture. So we had the expression for magnetic field from Swagat as mu naught by 4 pi integration of I dl cross r cap upon r square. That's all. Then this was for a single current where current I is flowing and this is the direction of dl. Now if I have a continuous distribution of current, then I will I will have something like this, maybe with varying cross section. So here currents are flowing, and I define a quantity J, which is current per unit area, and the direction is perpendicular to the area. This is J, this is n cap. Then if I take a dot product of n cap on both the sides, I get J dot n cap equals to di by dA. So my I becomes integration of J dot n cap dA, which is equals to integration of J dot ds vector. Very clear. Then we take it and put it here. As we put it here, we get B equals to mu naught by 4 pi triple integral of J cross r cap upon r square. This was the derivation which we were doing.
Yeah.
Then from here we can take just curl of B, and we can derive curl of B equals to mu naught J, and we can take delta dot B, which will come out to be 0.